Have you ever looked up at the night sky and wondered if everything you see, everything you know, is just an illusion? What if I told you that right now, at this very moment, you might be living inside the most extreme object in the universe, a black hole? It sounds absolutely insane, doesn't it? But here's the thing. Some of the brightest minds in physics are seriously considering this possibility. And the evidence they've gathered is both terrifying and mind-blowing. Picture this. You're sitting in your room, reading this script, thinking you understand reality. But what if the entire universe, every star, every galaxy, every atom in your body, exists within the event horizon of a massive black hole from a parent universe we can never see or interact with? What if the Big Bang wasn't the beginning of everything, but simply the moment when matter exploded inward through a black hole's singularity, creating our universe inside of it? Before you dismiss this as science fiction, let me tell you something that'll make your head spin. Scientists have discovered that the mathematics describing the Big Bang and the equations governing black hole singularities are eerily similar. In fact, they're so similar that some physicists argue they might be describing the same phenomenon from different perspectives. It's like looking at the same object from two different mirrors. The reflection appears different, but it's the same thing underneath. But let's start from the beginning. To understand why we might be living inside a black hole, we first need to understand what black holes really are. And trust me, they're far stranger than you've ever imagined. Most people think of black holes as cosmic vacuum cleaners, sucking up everything in sight like some kind of universal garbage disposal. But that's not quite right. Black holes are actually the remnants of massive stars that have collapsed under their own gravity to a point so dense that the fabric of space and time itself breaks down. Imagine taking Mount Everest and compressing it down to the size of a grain of sand. Now imagine doing that with an entire star that's 20 times more massive than our Sun. That's the kind of density we're talking about. At the center of every black hole lies something called a singularity, a point where all the mass of the black hole is compressed to infinite density and zero volume. Here's where things get weird. At the singularity, our understanding of physics completely breaks down. Time and space swap roles. The equations that describe everything else in the universe simply don't work anymore. They give us infinities, impossibilities, and nonsensical answers. Sound familiar? Because that's exactly what happens when we try to describe the moment of the Big Bang. When we rewind the history of our universe backward through time, everything gets smaller and denser, until we reach a point about 13.8 billion years ago, where the entire universe was compressed into an infinitely small, infinitely dense point. A singularity, the exact same mathematical impossibility that exists at the center of every black hole. This similarity isn't just a coincidence. It's what first got scientists thinking. What if the Big Bang singularity and a black hole singularity are the same thing? What if our universe didn't explode outward into empty space, but rather exploded inward through a black hole's event horizon? Now, I know what you're thinking. How could we possibly be inside a black hole if we're not being crushed into oblivion? How can we see stars billions of light years away if we're trapped inside something that doesn't even let light escape? These are excellent questions, and the answers are going to challenge everything you thought you knew about reality. The key lies in understanding what the inside of a black hole really means. When we talk about being inside a black hole, we're not talking about being in some kind of cosmic prison cell with walls pressing in on us. We're talking about being in a region of space where the geometry itself has been so warped and twisted that the normal rules simply don't apply anymore. Here's something that'll blow your mind. According to Einstein's general relativity, once you cross the event horizon of a black hole, time and space switch places. The direction toward the singularity doesn't point in space anymore, it points in time. Just as you can't avoid moving forward in time outside a black hole, you can't avoid moving toward the singularity once you're inside. But here's the crucial part. The singularity isn't a place you move toward in space. It's an event in your future, like next Tuesday. Now apply this to our universe. What if the Big Bang wasn't a point in space where everything exploded outward from? What if it was a moment in time, the moment when we all crossed through the event horizon of a massive black hole? From our perspective inside, we'd see space expanding in all directions, galaxies racing away from each other, exactly what we observe. But from the outside, in the parent universe, we'd simply be falling toward the singularity of their black hole, experiencing time dilation so extreme that our entire universe's lifetime would pass in the blink of an eye. This idea was first seriously proposed by physicist Nikodem Poplavsky in 2010, and it's called the cosmology from the inside of a black hole theory, though scientists often refer to it more technically as the Einstein-Cartangent-Siama-Kibble theory of gravity applied to black holes. That's a mouthful, so let's just stick with calling it the black hole universe theory. Poplavsky realized something remarkable. He was studying a modification to Einstein's theory of general relativity that includes something called torsion, a twisting of space-time fabric, not just a curving of it. Regular general relativity treats space-time like a rubber sheet that can be stretched and bent. But Einstein-Cartan theory treats it more like a piece of fabric that can also be twisted and spun. When Poplavsky applied this modified theory to black holes, something incredible happened. The singularity, that impossible point of infinite density, disappeared. Instead of all matter collapsing to a point of zero size, the equations showed that matter would reach a maximum density and then bounce back, exploding outward through what he called a wormhole. And on the other side of that wormhole, a new universe would be born. Let me paint you a picture of how this works. Imagine a massive star, perhaps 50 or 100 times the mass of our sun, reaching the end of its life in some parent universe. It collapses under its own gravity, forming a black hole. Matter spirals inward through the event horizon, falling toward the center. In regular general relativity, this matter would all pile up at an infinitely small point. But in Einstein-Cartan theory, when the matter gets compressed to about the Planck density, TMM, that's roughly 10 to the power of 94 grams per cubic centimeter, or basically the absolute maximum density that space itself can handle. Something remarkable happens. The spin of all that compressed matter creates enormous torsion forces that push back against gravity. It's like compressing a spring until it can't be compressed anymore. Eventually, the spring pushes back. In this case, space-time itself pushes back against the collapse. The matter stops shrinking and violently expands, creating what Poplavsky calls a big bounce. But here's the crucial part. This expansion can't happen back into the parent universe. The event horizon prevents anything from escaping. So instead, the expansion creates a new region of space-time, connected to the black hole through a wormhole, but existing in its own separate domain. From the perspective of someone in the parent universe, they just see a normal black hole sitting there, maybe eating nearby matter. Maybe not. But from the perspective of someone inside the black hole, someone like us, we'd see an entire universe expanding from an incredibly hot, dense state. We'd call this moment the Big Bang. We'd see space expanding, galaxies forming, stars being born. We'd have no idea we were inside a black hole from a parent universe. This is where things get truly mind-bending. If our universe formed inside a black hole, then every black hole in our universe might be giving birth to new universes. Right now, at this very moment, Millions of black holes in our universe might be nurturing entire cosmoses inside them, each with their own stars, planets, and potentially civilizations, all wondering if they're living inside a black hole just like we are. Think about that for a second. The black hole at the center of our Milky Way, Sagittarius A star, weighing 4.6 million times the mass of our Sun, it might contain an entire universe inside it. And that universe might have its own black holes, each containing more universes, in an infinite nested hierarchy of cosmoses within cosmoses, like an endless set of Russian dolls where each doll contains not just another doll, but an entire universe of possibilities. But wait, I know what you're thinking. This all sounds like wild speculation. Where's the evidence? What makes this theory any more than just mathematical philosophy? Well, that's what makes this theory so exciting. It actually makes testable predictions, and some of those predictions might have already been confirmed. Let me tell you about one of the most intriguing pieces of evidence. According to Poplaski's theory, if our universe was born from a rotating black hole, and most black holes do rotate, then our universe should inherit that rotation. Just like a figure skater spins faster when they pull their arms in, the matter inside a black hole would be spinning incredibly fast. And when that matter bounced and expanded to form our universe, it should have carried that spin with it. Now, here's where it gets interesting. If the universe is rotating, then galaxies shouldn't be spinning randomly. There should be a pattern. Specifically, if you look at one hemisphere of the universe, you should see more galaxies spinning in one direction, and if you look at the opposite hemisphere, you should see more galaxies spinning in the other direction. It's like if you spun a pizza and then threw pepperoni on it. The pepperoni would show the rotation of the pizza underneath. In 2011, a team of physicists at the University of Michigan, led by Michael Longo, analyzed the rotation directions of over 15,000 galaxies. And guess what they found? In one part of the sky, galaxies preferentially rotated counterclockwise. In the opposite part of the sky, they preferentially rotated clockwise. The pattern matched exactly what you'd expect if the universe was rotating. The probability of this being a random coincidence was less than 1 in a million. Now, other scientists have disputed these findings, arguing that the pattern might be due to systematic errors in how galaxy rotations were measured. The debate is ongoing, but the fact that we can even test this prediction is remarkable. We're not just engaging in philosophical speculation here. We're doing real science with real data. Let's dig deeper into the mathematics behind this wild idea, because the numbers are where this theory really starts to get interesting. And don't worry, I'm not going to drown you in equations. Instead, I'm going to show you why the math behind our universe and the math behind black holes are so eerily similar that even skeptical physicists have to stop and wonder. First, let's talk about the cosmic coincidence that started this whole line of thinking. When physicists calculate the density of the universe at the moment of the Big Bang, they get a number around 10 to the power of 94 grams per cubic centimeter. That's a 1 followed by 94 zeros. It's so large that trying to visualize it is pointless. But here's the thing. That exact same number keeps popping up when physicists calculate the maximum density that can exist at the center of a black hole before quantum effects become impossible to ignore. This number is called the Planck density, named after Max Planck, one of the founders of quantum mechanics. It represents the point where gravity becomes so strong and space becomes so warped that our current theories of physics hit a wall. Below this scale, at what we call the Planck length, about 10 to the power of minus 35 meters, space itself might not even be continuous anymore. It might be grainy, pixelated, made up of discrete chunks that can't be subdivided further. The fact that the Big Bang density and the black hole singularity density are both at this Planck limit isn't just a coincidence. It's telling us something profound. It's suggesting that whatever happened at the Big Bang and whatever happens at the center of a black hole are related phenomena. They're both situations where matter gets compressed to the absolute maximum density that reality can handle. But here's where the theory goes further. In standard Einstein relativity, when you calculate what happens at a singularity, you get infinities. The density becomes infinite, the curvature of space-time becomes infinite, and our equations literally break down and give us nonsensical answers. Physicists call this a pathology, a sign that something is wrong with our theory, not with reality itself. But when you add certain corrections to the equations, modifications that account for quantum effects, something remarkable happens. The infinities disappear. Instead of the density becoming infinite, it reaches a maximum value and then starts decreasing. The matter doesn't collapse to a point, it bounces back. And most remarkably, the equations predict that this bounce creates a new expanding region of space-time on the other side of the event horizon. Let me put this in more concrete terms. Imagine you're watching a star collapse into a black hole from the outside. You see the star shrink smaller and smaller, but because of time dilation, you never actually see it cross the event horizon. From your perspective, time for the star slows down so much that it appears to freeze just at the edge of the black hole, slowly fading to black as its light gets redshifted into invisibility. But from the perspective of matter falling into the black hole, something completely different happens. As the matter crosses the event horizon and falls inward, it gets compressed more and more. But instead of reaching infinite density at a single point, it reaches the Planck density and bounces. This bounce is incredibly violent. Imagine all the matter of a massive star compressed to nuclear density, suddenly expanding at near light speed. But here's the key. This expansion can't go back out through the event horizon. Nothing can escape from inside a black hole, not even an explosion that would make a supernova look like a firecracker. So where does this expanding matter go? According to the equations, it creates a new region of space-time, a new universe, connected to the parent universe only by a thin tunnel, a wormhole, at the location of what would have been the singularity. From inside this new universe, observers would see exactly what we see when we look at our own universe. They'd see space expanding in all directions. They'd see a cosmic microwave background, the afterglow of that initial explosion. They'd see matter cooling and forming into hydrogen and helium, then into stars and galaxies. They'd have no idea they were inside a black hole unless they did the math and realized their universe's properties matched what you'd expect from a black hole interior. Now, you might be wondering, if we're inside a black hole, why does space look flat and infinite? Why don't we see the walls of the black hole or feel like we're in some kind of enclosed space? The answer has to do with the bizarre geometry of black hole interiors. Outside a black hole, space curves around it. Like a funnel, the closer you get to the event horizon, the more space is warped. But once you cross the event horizon, something strange happens. Space and time swap roles. The direction toward the singularity becomes a direction in time, not space. And the dimensions that were spatial outside become temporal inside. This means that from inside the black hole, you don't see the singularity as a point in front of you that you're falling toward. You see it as a moment in your future that you're inevitably moving toward, just like you inevitably move toward tomorrow. And in the meantime, space can expand around you in all three spatial dimensions, just like it does in our universe. Think of it this way. Imagine you're in a car driving toward a cliff. Outside the car, the cliff is a place, a specific location in space that you're moving toward. But now imagine that crossing the cliff edge somehow transforms the cliff from a place into a time. It's no longer somewhere you're going, it becomes sometime you're going. That's what happens when you cross a black hole's event horizon. The singularity transforms from a place to a time. This weird property of black hole geometry actually solves one of the biggest problems with the Big Bang theory. In standard cosmology, we have to ask, what came before the Big Bang? If the universe began at a single point and exploded outward, what was there before that moment? What caused the explosion? Where did all that energy come from? These questions have plagued physicists for decades. Some suggest there was nothing before the Big Bang. That time itself began at that moment. But this feels unsatisfying. Others suggest an infinite regress. Perhaps there was another universe before ours, which collapsed and then rebounded in a Big Bang. But this just pushes the question back further. Where did that previous universe come from? The black hole universe theory provides an elegant answer. There was something before the Big Bang, the parent universe. Our universe didn't come from nothing. It came from a massive star collapsing in that parent universe. The energy of our Big Bang came from the gravitational potential energy of that collapsing star. And the reason we can't see or interact with the parent universe isn't because it doesn't exist, but because we're trapped inside the event horizon, where the laws of causality prevent any information from flowing backward out of the black hole. But here's where things get even more interesting. If our universe came from a black hole in a parent universe, then logically, that parent universe might have come from a black hole in its parent universe, and that universe from another black hole before it. You could have an infinite chain of universes, each giving birth to new ones through black holes, stretching backward in time forever. This actually solves the problem of infinite regress in an interesting way. Instead of having to explain where the first universe came from, you don't need a first universe at all. The chain of causality extends infinitely backward, with no beginning and no end. Every universe is both a child of a previous universe and a parent of future universes. It's cosmology as biology. Universes reproducing, evolving, each one slightly different from its parent based on the conditions of the black hole that birthed it. But let's get back to the mathematics for a moment, because there's another equation that provides stunning support for the black hole universe theory. It's called the Schwarzschild radius, and it tells you how large a black hole's event horizon is based on its mass. The equation is simple. The radius equals 2 times the gravitational constant times the mass, divided by the speed of light squared. Now, here's something incredible. If you take the total mass of the observable universe, all the stars, all the dark matter, all the energy, everything, and plug it into this equation, you get a number for the Schwarzschild radius. And that number is approximately equal to the size of the observable universe itself. In other words, our universe has exactly the right amount of mass and exactly the right size to be a black hole. Let me repeat that, because it's important. The observable universe, with its roughly 10 to the 53 kilograms of mass spread across 46 billion light-years, has the same mass-to-size ratio as a black hole. If you were an observer in the parent universe looking at the black hole that contains our universe, you'd calculate its event horizon to be right about where we see the edge of our observable universe. Now, skeptics will point out that this could just be a numerical coincidence. After all, the universe has the mass it has and the size it has, and maybe it's just chance that they happen to match the black hole equation. But when you're a scientist and you see your theory making a prediction that turns out to be true to within a factor of 2 or 3, you start paying attention. It's like if someone told you they could predict the weather, and then for 10 days in a row, they got it right within a few degrees. At some point, you stop calling it luck and start calling it a working theory. there's another mathematical clue that's even more intriguing. When physicists calculate the entropy of a black hole, basically the amount of information or disorder it contains, they find something strange. The entropy doesn't depend on the volume of the black hole, but on the area of its event horizon. It's as if all the information about what's inside the black hole is somehow encoded on its two-dimensional surface, like a hologram. This led to the holographic principle, which suggests that our three-dimensional universe might actually be a projection of information encoded on a two-dimensional surface. It sounds like science fiction, but the mathematics works out beautifully. And if our universe is the interior of a black hole, then this makes perfect sense. All the information about our universe would be encoded on the event horizon of the black hole, as viewed from the parent universe. We, living inside, experience this information as a three-dimensional cosmos, but from outside, it's all written on a two-dimensional surface. Think about that for a moment. Everything you've ever experienced, every thought you've had, every star you've seen in the sky, all of it might be information encoded on the surface of a black hole in some higher universe. You're not really a three-dimensional being moving through three-dimensional space. You're a pattern of information on a two-dimensional surface, experiencing yourself as three-dimensional. It's enough to make your head spin, isn't it? But the mathematics keeps leading us back to the same conclusion. Our universe has all the properties we'd expect if it were the interior of a black hole. The mass-to-size ratio matches. The entropy matches. The behavior near the Big Bang matches the behavior near a singularity. The expansion of space matches what you'd see inside an event horizon. And so still, almost 300 years after they were first proposed, nothing in the universe is as mysterious as a black hole. So far, we've been dancing around theoretical physics and abstract mathematics. But if we really are living inside a black hole, there should be observable evidence, things we can actually measure and test. And incredibly, when scientists started looking for this evidence, they found patterns in the cosmos that are difficult to explain with standard Big Bang theory, but make perfect sense if we're inside a black hole. Let's start with one of the most perplexing mysteries in modern cosmology: the uniformity of the cosmic microwave background radiation. This is the afterglow of the Big Bang, a faint microwave signal that comes from every direction in the sky, left over from when the universe was only 380,000 years old. When scientists first mapped this radiation in detail using satellites like COBE and WMAP, they discovered something shocking. The temperature of this radiation is almost perfectly uniform across the entire sky. No matter which direction you look, the temperature is 2.725 Kelvin, give or take a few thousandths of a degree. This uniformity is remarkable, but it's also deeply problematic for standard Big Bang theory. Here's why. For two regions of space to have the same temperature, they need to have been in contact with each other at some point. Heat needs to flow between them until they reach equilibrium. But when you calculate how much of the universe could have been in contact during the first 380,000 years after the Big Bang, you find that regions on opposite sides of the sky couldn't possibly have communicated with each other. They're too far apart. Even traveling at the speed of light, there wasn't enough time for heat or any information to flow between them. So how did they end up at exactly the same temperature? Standard cosmology solves this problem with something called inflation, a period of exponential expansion in the first fraction of a second after the Big Bang that stretched a tiny uniform region of space to cosmic scales. Inflation works mathematically, but it feels like adding a fix created specifically to solve the problem without any independent motivation. But the black hole universe theory offers a different explanation. If our universe formed inside a rotating black hole, then all the matter and energy came from a single source: the collapsing star in the parent universe. Before that matter crossed the event horizon, it had time to reach thermal equilibrium. It all came from the same place and was in contact with itself. When it bounced and expanded to form our universe, it naturally carried that uniform temperature with it. In other words, the cosmic microwave background is uniform for the same reason a cup of coffee is uniform. All the liquid came from the same pot and had time to mix before you poured it. No inflation required. The uniformity of our universe is simply a consequence of its origin from a single thermally equilibrated source. But there's more. Remember I mentioned that rotating black holes should impart their spin to the universe they create? Well, that rotation should leave signatures beyond just galaxy spin patterns. It should affect the cosmic microwave background itself. When physicists analyzed the detailed structure of the cosmic microwave background, they found something called the axis of evil. Don't let the dramatic name fool you. It's just what astronomers called an unexpected alignment in the data. The largest temperature fluctuations in the cosmic microwave background aren't randomly distributed across the sky. They're aligned along a particular axis, and that axis points in a specific direction through space. This is weird, really weird. In standard Big Bang cosmology, there's no reason for the universe to have a preferred direction. Space should look the same in all directions. But if our universe is rotating because it formed from a rotating black hole, then suddenly this axis makes sense. It's the rotation axis of the parent black hole, and we're seeing its imprint on the oldest light in our universe. Now, I need to be careful here. Some physicists dispute the significance of the axis of evil. They argue it might be a statistical fluke, but others take it very seriously. The probability of such an alignment occurring by chance in a truly isotropic universe is less than 1%. Let's talk about another piece of evidence: dark energy. This is the mysterious force that's causing the universe's expansion to accelerate. About 5 billion years ago, something strange happened. The universe had been expanding, but that expansion was slowing down due to gravity. Then suddenly, the expansion started speeding up. Galaxies began racing away from each other faster and faster, as if space itself was being inflated from within. Dark energy makes up about 68% of the total energy content of the universe, but we have no idea what it is. It's not matter, it's not radiation, it's just there, pushing space apart. But here's something fascinating. The acceleration of our universe's expansion matches almost exactly what you'd expect if our universe was expanding inside a black hole whose own event horizon was growing. When a black hole absorbs matter, its event horizon grows. The Schwarzschild radius increases proportionally to the mass. From inside the black hole, we can't see the event horizon directly. We're inside it, remember? But we should feel its effects. As the event horizon of the parent black hole expands due to matter falling in from the parent universe, the space inside, our universe, would need to expand too. And this expansion would appear to us as an accelerating expansion driven by dark energy. Think of it like this. Imagine you're inside a balloon, and someone is blowing up the balloon from outside. You can't see the person blowing or the rubber of the balloon, but you'd notice that everything around you is spreading apart faster and faster. That's what dark energy might be, the signature of matter falling into the black hole that contains our universe, causing its event horizon to grow. This explanation is elegant because it doesn't require inventing a new form of energy with bizarre properties. Dark energy isn't a thing. It's an effect of our universe's boundary expanding as the parent black hole grows. Let me tell you about another strange cosmic mystery that the black hole universe theory helps explain: the flatness problem. When physicists measure the geometry of our universe, whether space curves back on itself like the surface of a sphere, stretches out like a saddle, or remains flat like a sheet of paper, they find that it's almost perfectly flat. so flat that we can't detect any curvature even when we look at regions billions of light years across. This flatness is incredibly improbable. In the standard Big Bang theory, the universe could have had any curvature. The odds of the universe being this flat by chance are astronomically small, like balancing a pencil on its point and having it stay balanced for billions of years. The black hole universe theory offers a more natural explanation. If our universe formed inside a black hole, its geometry would be determined by the geometry of the black hole's interior. And remarkably, the interior of a large black hole is very close to being flat. The curvature is there, but it's so gentle that it would be imperceptible to anyone living inside. So our universe is flat, not because of some extraordinary coincidence or because of a period of rapid inflation. It's flat because we're inside a very large black hole, and the interior geometry of large black holes is nearly flat. Simple, elegant. There's one more piece of evidence I need to tell you about: the cosmic horizon. When we look out into space, we can only see so far. Beyond a certain distance, about 46 billion light years in all directions, we can't see anything. Not because there's nothing there, but because light from farther away hasn't had time to reach us yet. This horizon is called the cosmic horizon, and in standard Big Bang cosmology, it exists simply because the universe has a finite age. But here's something interesting. This horizon looks suspiciously like an event horizon. Beyond it, we can't receive any signals. We can't see what's happening there. We can't interact with it. It's a one-way barrier in space-time. Now, if we're inside a black hole, this cosmic horizon might actually be the event horizon of that black hole. The edge of our observable universe might be the edge of the black hole that contains us. We can't see beyond it not just because light hasn't had time to reach us, but because light from outside the black hole can't cross the event horizon to reach us. This would explain why the size of our observable universe matches so closely with the Schwarzschild radius of a black hole with the same mass. It's not a coincidence. The observable universe is the black hole. The horizon we see is the event horizon. We're looking at the boundary of our cosmic prison, not realizing that what we think is a limit of observation is actually a wall of reality itself. Now that we've explored the evidence, let's talk about what this all means. Because if we're living inside a black hole, and every black hole creates a new universe, then we're not just talking about one or two universes. We're talking about an infinite number of universes nested inside each other, branching out like the roots of an impossibly vast tree. And each universe might have its own laws of physics, its own constants of nature, its own possibilities for what can exist. Let me take you on a journey through this cosmic tree. Start here, with our universe. Right now, at this moment, there are millions of black holes in our observable universe alone. At the center of our Milky Way, there's Sagittarius A star, weighing 4.6 million times the mass of our Sun. In the galaxy Messier 87, there's a supermassive black hole 6.5 billion times the mass of our Sun, the first black hole ever photographed. In the distant quasar Taun 618, there's a monster black hole 66 billion times the mass of our Sun. According to the black hole universe theory, each of these black holes contains a universe, not will contain, contains, right now. The universes inside them have already been born, are already evolving, perhaps already have stars and planets and maybe even civilizations, wondering if they're living inside a black hole. But it gets more mind-bending. Those universes inside our black holes, let's call them child universes, would have their own black holes, and those black holes would contain their own universes, grandchild universes, and those would have black holes containing great-grandchild universes. The chain extends downward infinitely, each generation containing countless universes, each universe containing countless black holes, each black hole birthing new universes. Now, go the other direction. Our universe exists inside a black hole in a parent universe. But that parent universe exists inside a black hole in a grandparent universe, and that exists inside a great-grandparent universe. The chain extends upward infinitely too. We're not at the top or the bottom. We're somewhere in the middle of an infinite hierarchy, with infinite generations of universes above us and infinite generations below us. Try to visualize this. It's almost impossible, isn't it? Every point in space in our universe where a black hole exists is actually a doorway to an entire cosmos. And we ourselves might be inside such a point in the parent universe. From their perspective, we're smaller than an atom, but from our perspective, we're 93 billion light years across. Scale loses all meaning. What's big and what's small depends entirely on which side of the event horizon you're on. But here's where it gets truly fascinating. Each of these universes might have different laws of physics. When matter collapses through a black hole and bounces to form a new universe, the properties of that new universe would depend on the properties of the collapsing matter. Things like how much angular momentum it had, how much charge, what its quantum state was. These properties would influence the physical constants in the new universe. Things like the strength of gravity, the mass of the electron, the speed of light. In our universe, the electron has a particular mass. Gravity has a particular strength. These values seem arbitrary. We don't know why they are what they are, but in the black hole universe theory, these values were set by the conditions of the collapsing star that gave birth to our universe. And in other universes born from different black holes under different conditions, these constants would have different values. This means that some child universes might have gravity that's stronger than ours. In those universes, stars would burn faster and die younger. Other child universes might have weaker gravity, where stars burn slowly, where it takes longer for structures to form. Some universes might have electrons that are heavier, which would change the structure of atoms and make chemistry completely different. Other universes might have different nuclear forces, changing how protons and neutrons stick together, altering which elements can exist. And some universes, perhaps most universes, might have physical constants so different from ours that nothing interesting can happen. Maybe gravity is so strong that everything collapses immediately into black holes. Maybe the electromagnetic force is so weak that atoms can't hold together. These universes would be sterile, empty, boring. This leads to a profound realization. We exist in a universe with the constants it has not because these constants are special or fundamental, but because we can only exist in a universe where the constants allow for our existence. It's a selection effect. There might be billions or trillions of universes with different constants, but we naturally find ourselves in one of the rare universes where stars can form, where chemistry is complex enough for life, where evolution has time to work. This is sometimes called the anthropic principle. In the black hole universe theory, the anthropic principle isn't giving up. It's a natural consequence of the reproductive mechanism of universes. Think of it like biological evolution. Why do fish have gills? Because fish without gills couldn't breathe water and died before reproducing. Similarly, our universe has the constants it has because universes with very different constants either don't produce black holes or produce them very inefficiently and therefore have fewer offspring universes and therefore become rare in the cosmic family tree. Universes evolve, not through time. Each individual universe has its own time that doesn't connect to other universes' time, but through generational descent. Child universes inherit their physical constants from their parent universes, with small variations depending on the specific conditions of the black hole that birthed them. And universes with constants that make them good at producing black holes leave more descendants. Over countless generations, the multiverse becomes dominated by universes optimized for black hole production. And what kind of universes are good at producing black holes? Universes like ours. Universes where stars can form and live long enough to enrich space with heavy elements, but then die violently enough to collapse into black holes. We're not in a typical universe. We're in a survivor universe. A universe whose lineage has been shaped by billions or trillions of generations of cosmological selection to be good at making black holes. And as a side effect, this makes our universe good at making complex chemistry, stable stars, planets, and eventually, life. Now, here's something that will really blow your mind. If this theory is correct, then consciousness might not be rare in the multiverse. It might be common. Because universes that produce conscious beings are probably also good at producing black holes. Think about it. What does it take for consciousness to evolve? You need stable stars that live for billions of years. You need a rich chemistry with many different elements. You need planets where complex molecules can form and evolve. But these are the exact same conditions that lead to the formation of massive stars that eventually collapse into black holes. The requirements for life and the requirements for black holes overlap substantially. This means that in the vast majority of successful lineages in the cosmic tree, consciousness is likely to be common. Not because the universe is designed for consciousness, but because consciousness is a side effect of the same conditions that make universes good at reproducing through black holes. You, right now, reading this script, you're a side effect of cosmological evolution. Your existence is a consequence of billions of generations of universes learning, through trial and error and natural selection, how to make black holes efficiently. In a sense, we're living proof that our universe comes from a successful lineage. The very fact that we exist to ask these questions suggests that our universe has the characteristics of a survivor, a universe shaped by countless generations of cosmological selection. But there's something else we need to consider. If every black hole creates a universe, then the total number of universes is almost beyond comprehension. In our observable universe, there are roughly 100 billion galaxies. Each galaxy has, on average, about 100 million black holes. That's 10 to the 19th power, 10 billion black holes in our observable universe. And that's just what we can see. Each of those black holes contains a universe, and each of those universes contains a similar number of black holes. And each of those contains a universe. After just a few generations, you have more universes than there are atoms in our entire observable universe. And remember, this chain extends infinitely both upward and downward. The number of universes in the complete multiverse would be not just infinite, but infinitely infinite. It's what mathematicians call a higher order infinity, an infinity of infinities. Each of those universes is a complete cosmos, with its own physics, its own history, potentially its own life and consciousness. Some of them might be very similar to ours, but other universes would be completely alien. Universes where the laws of physics are so different that nothing familiar could exist. And here's something that really challenges our intuition. All of these universes are equally real. The child universes inside black holes in our universe are just as real as we are. The parent universe that contains our universe is just as real as we are. There's no hierarchy of reality. This means that the multiverse isn't just big. It's not just diverse. It's absolutely teeming with existence, with reality, with possibility. Every conceivable variation of physical laws that can produce black holes exists somewhere in this infinite tree. The multiverse doesn't just contain everything that exists, it contains everything that could exist. We've journeyed deep into one of the most radical ideas in modern physics, that our universe might be the interior of a black hole, nested within an infinite hierarchy of universes creating and being created through black holes. But now, we need to confront the hard questions. What does this theory really tell us? How can we test it? And perhaps most importantly, what does it mean for us, for our understanding of reality, our place in the cosmos, and the ultimate fate of everything we know? Let's start with the elephant in the room. Can we ever truly prove that we're living inside a black hole? This is where the theory runs into some serious philosophical and practical problems. The fundamental challenge is that the event horizon is a one-way barrier. Nothing can cross from inside a black hole to outside. No light, no particles, no information of any kind. This means that even if we are inside a black hole, we could never communicate with the parent universe. We could never send a probe outside to look back at ourselves. We could never run an experiment that directly detects the event horizon or measures the properties of the parent universe. From a scientific perspective, this is deeply frustrating. Science advances through testing predictions, through experiments that can distinguish between competing theories. But how do you test a theory when the thing you're trying to detect is fundamentally undetectable from your vantage point? Some philosophers of science would argue that this makes the black hole universe theory unfalsifiable and therefore unscientific. If no experiment could ever disprove it, then it's not really physics, it's metaphysics. But defenders of the theory argue that it's not completely unfalsifiable. Remember those predictions we discussed? The rotation of galaxies, the axis of evil in the cosmic microwave background, the specific pattern of the universe's expansion? These are testable predictions. The problem is that most of these signatures can also be explained in other ways. In science, we often have to choose between competing theories that all explain the same data. And usually, we choose based on Occam's razor, the principle that simpler explanations are better than complicated ones. Standard Big Bang cosmology with inflation and dark energy requires us to introduce two entirely new entities: an inflaton field that only existed for a tiny fraction of a second and dark energy, a mysterious force that makes up 68% of the universe. The black hole universe theory, on the other hand, only uses physics we know exists: general relativity, quantum mechanics, black holes. So which is simpler? Reasonable people can disagree. Now let's talk about what this theory means for the ultimate fate of our universe. In standard cosmology, the universe faces a cold, dark future. The expansion will continue accelerating forever. Stars will burn out. Black holes will evaporate through Hawking radiation. Eventually, the universe will be a cold, empty expanse. Physicists call this the heat death of the universe. But in the black hole universe theory, things are different. If we're inside a black hole, then our ultimate fate is determined by what happens to that black hole. And black holes don't last forever. Stephen Hawking showed that black holes emit radiation, causing them to slowly lose mass and shrink. For a stellar mass black hole, this process takes roughly 10 to the 67th years. But if our universe is inside a black hole, and that black hole is evaporating, what happens to us? The answer depends on the relationship between time inside the black hole and time outside. If time inside is completely disconnected from time outside, then the evaporation might not affect us at all. Our universe might live its entire life in what appears from outside to be just a brief moment. Alternatively, as the parent black hole shrinks, our universe might shrink too. The expansion might reverse. Instead of accelerating forever, we might eventually start contracting. falling back together in a big crunch. Unless future civilizations can create black holes of their own and somehow transfer themselves into the universes inside those black holes before the collapse arrives. This would be the ultimate form of cosmic escape, jumping from a dying universe into a newly born one. It sounds like science fiction, but in a multiverse where every black hole contains a universe, it might be the only form of immortality available. If we are living inside a black hole, then we're fundamentally cut off from the larger reality. The parent universe is not just far away, it's fundamentally inaccessible. We can never visit it, never see it, never communicate with it. The event horizon is an absolute barrier. This means that our universe is, in a sense, a prison. For some people, this idea is terrifying, but for others, it's strangely comforting. Yes, we're in a black hole, but it's our black hole. This universe is our home, complete and self-contained. And if every black hole in our universe contains its own cosmos, then we're surrounded by universes. They're here, wherever black holes exist. The supermassive black hole at the center of our galaxy contains a universe. They're our neighbors, our children in the cosmic family tree, even though we can never meet them. This gives our existence a new kind of meaning. We're part of a vast network of creation, a tree of universes branching and growing through black hole formation. And if this theory is true, then every moment of your existence is part of something unimaginably vast. You're not just a human on a planet. You're a pattern of information in a universe inside a black hole in a parent universe, extending upward forever. And you're living in a universe that contains black holes with child universes, extending downward forever. So the next time you look up at the night sky, remember, those stars are potential parents of future universes. And the darkness between them is dotted with black holes, each one a doorway to an entire cosmos. We're living proof that black holes aren't destroyers, they're creators. Are we living inside a black hole? The math says maybe, the evidence is suggestive, the implications are staggering, and the truth is, we may never know for certain. But just asking the question forces us to confront how little we understand about reality. Maybe someday, future physicists will find definitive proof. Or maybe this will remain one of those questions that sits at the boundary of science and philosophy, forever tantalizingly close to being answered, but never quite within our grasp. Either way, the journey has been worth it, because the universe doesn't owe us simple answers. It can be strange, counterintuitive, so far beyond our everyday experience that we need advanced mathematics just to describe it. But it can also be comprehensible. We might never understand everything. We might be forever trapped inside our cosmic black hole, cut off from the larger reality. But within the boundaries of our universe, we can still explore, discover, understand. And that's not a prison. That's an adventure. So yes, we might be living inside a black hole, but you don't feel it, do you? And that's the final wonder of it all. Even if we're inside the most extreme object in the cosmos, it still feels like home. Because it is home. Thank you for joining me on this journey through one of the strangest ideas in modern physics. Keep looking up, keep asking questions, and never stop wondering about the true nature of reality. Because the universe, black hole or not, is far more amazing than we ever imagined.